Hello everyone. Today we'll talk about another applications of equation of motion. During last lessons we derived the most general form of equation of motion and we use it in uniform motion. Now it's time for vertical projection. We have two balls, the first and the second. The initial distance between these balls is h equal to 200 meters, and in the same moment we throw these balls vertically, the first ball downward with velocity v1, magnitude of this velocity is 20 meters per second, and the second ball we throw upward with velocity v2, magnitude of this velocity is equal to 80 meters per second. So that it was easier to calculate, we'll assume that gravitational acceleration g is equal 10 meters per second square. In this task, we want to know where and when these balls will meet. To solve this problem, we use equation of motion. I'll remind you the most general form of equation of motion. It is here. Usually here we write x and here x, but we named our axis h, so here is h and here is h. We have to know the meaning of h0, v0 and a. So h0 is a coordinate of initial position of the body, v0 is a coordinate of initial velocity vector, so I should remind you what does it mean. The coordinate of the vector is equal to plus magnitude of the vector if vector is directed the same as axis, or minus magnitude of vector if vector is opposite to the axis. And a is a coordinate of acceleration vector, and the same here if coordinate of acceleration vector is equal to plus magnitude of acceleration vector, or minus if the vector is directed the same as axis, or minus magnitude of acceleration vector if this vector is opposite to the axis. So now we can write equation of motion for first and second body. Before we do it, we should draw also acceleration vectors for first and the second body. We know from the second Newton's law of motion that acceleration vector is directed the same as resultant force. Here the only acting force on the first and the second body is a gravitation force, so it is directed downward, and the same is the direction of acceleration vector, a1 and a2. We know from the second Newton's law of motion that magnitude of acceleration vector is equal magnitude of resultant force divided by a mass. In this task we assume that in frame of reference connected with surface of Earth is inertial frame of reference, and we can replace force of gravity by weight, and weight is equal to mass multiplied by g, gravitational acceleration. If we divide weight, this is mass times gravitational acceleration by mass, mass will cancel and will achieve g. So in both cases a magnitude of acceleration for the first and the second body is equal to gravitational acceleration g. So now we can write equations of motion for the first and the second body. Let's start. h1 equals to initial coordinate of position of the first body. Let's see, here is the first body, and initial coordinate of position is equal to h. It's h because we choose the initial position of initial coordinate of position for the second body to 0. 0 plus h equals to h. Next, here is minus because velocity vector v1 is opposite to the axis h, so its coordinate is equal to minus magnitude of this vector, minus v1 times delta t. We can here write also t. It is often used in this place. When we can replace delta t by t, if both bodies begin to move in the same moment, then we can write instead of delta t, t, and it will be equally good. And we see that the first body changes its velocity, so we have acceleration vector, and we see that acceleration vector is also opposite to the axis. So here we have minus. Because coordinate of acceleration vector a1 is equal to minus magnitude of this vector, minus a1 and is equal to g, the gravitational acceleration. So here we have minus g and multiplied by delta t squared divided by 2. And we have the first equation of motion for the first body. Then we write equation of motion for the second body. Initial coordinate of position for the second body is equal to 0. So here we have 0. Velocity vector, initial velocity vector v2 is directed the same as axis h, so its coordinate is positive and is equal to plus magnitude of this vector. So here we have plus v2, where v2 is magnitude of initial velocity vector v2. Next, we see that acceleration vector a2 is opposite to the axis, so its coordinate is negative and is equal to minus magnitude of this vector. This is minus g. So here is minus g times delta t squared divided by 2. So we have equation of motion for the second body, and equations of motion allow us to find coordinate of position of the body in any moment. If we know initial magnitude of initial velocity and we know magnitude of acceleration, and we put here the time that elapsed from the beginning of the motion, then we'll have the knowledge where we'll find this body on the axis h. Now we want to know where and when these balls will meet. And we know that in the moment when they meet, they will be in the same place. So h1 equals to h2. We put, instead of h1 and h2, right sides of these equations. It's done here. Instead of h1, we put that expression. Instead of h2, we put this expression. We see that this last expression will cancel if we change sides of this equation, and we can change form of this equation to such, and can transform this to this form and calculate delta t. We know height, we know magnitudes of velocities, so we put here, and we know now that these balls will meet after 2 seconds. If we want to know where these balls will meet, it is enough to put this value to first equation or to the second equation, and it's done here. To the first equation, we instead of delta t here and here, we put 2 seconds. 2 seconds squared, it's 4 seconds c squared. And we see that we achieve the same value. After 2 seconds, these balls met, so they were in the same place. So coordinate of position of both bodies was the same. So now we can solve any problem similar to that. I mean, when we are throwing 2 bodies vertically, only if we know velocity vector v1, v2 and acceleration vector, and if we know what sign to write here and here. And I remind you that v0 and a are coordinates of vectors, so they can be positive or negative. They are positive if vector v0 or a is directed the same as axis, or are equal to minus magnitude of vector if v0 or acceleration vector are directed opposite to the axis. So we solved our problem. It's all for today, but I remind you that you can find other lessons on the playlist named Kinematics and Dynamics. There is also one more playlist with lessons recorded in English. It's named Special Theory of Relativity. That second playlist contains all lessons recorded in English. So it's the end of this lesson. Hello everyone. This is next lesson about applications of equation of motion. During last lessons we derived the most general form of equation of motion, and we used it in projectile motion. When we throw the body vertically, upward or downward, or diagonally at some angle to the horizontal. We also used equation of motion in uniform motion. In this task we are throwing a body horizontally at the height h. We assume that frame of reference connected with the surface of Earth is inertial frame of reference, and then we can replace force of gravity by weight. We also assume that there is no resistance, so the front body is moving the same as in the vacuum. We know from the second Newton's law of motion that acceleration vector is directed the same as resultant force. In this case, the only acting force is force of gravity, and it is directed downward, so the same is directed acceleration vector. Also from the second Newton's law of motion, we can calculate magnitude of acceleration vector. It is magnitude of weight divided by mass. Weight is equal mass times g. G is gravitational acceleration, so m times g divided by m cancels, and we have the result that magnitude of acceleration vector is equal to g, to gravitational acceleration. In this task we want to know where the thrown object will hit the obstacle. This obstacle can be a horizontal platform, vertical wall, or a slope. Equation of a platform is y equals to b, if here is b. Equation of vertical wall is x equals to c, if here is c. Equation of a slope is y equals tangent beta, this is this angle, times x. This method is simple. We want to write equation of the path of the front body in the coordinate system y, x, and we'll write equations of describing the obstacle, this, or this, and we'll try to find the place of intersection of these two lines. To write equation of the path of the front body, we'll write equation of motion for the axis x and equation of motion for the axis y. Let's start with the equation of motion for the axis x. Here I wrote the most general form of equation of motion, and here we have to know the meaning of x0, v0 and a. So I remind you that x0 is coordinate of initial position, v0 is coordinate of initial velocity vector, and a is coordinate of acceleration vector. I should also remind you that coordinate of vector is equal to plus magnitude of vector if vector is directed the same as axis, or minus magnitude of vector if the vector is opposite to the axis. So we should remember that x0, v0 and a can be positive or negative. It is very important to draw velocity vector and acceleration vector, because otherwise we wouldn't know if v0 or a are positive or negative. So let's start to write equation of motion for the axis x. We see that coordinate of initial position on the axis x of the front body is 0. So x0 is equal to 0. The body has velocity in the direction of the axis x, it is v0, and v0 is directed the same as axis x, so coordinate of this vector is equal to plus magnitude of this vector. So here we have plus v0. So x equals plus v0 times delta t. We see that in the direction of the axis x there is no acceleration because there is no force acting in this direction. So acceleration vector does not have component in the axis x, so it is equal 0. So equation of motion for the axis x is just x equals v0 times delta t. Now we can write equation of motion for the axis y. We see that coordinate of initial position on the axis y is equal to h. So here is h. There is no velocity in the direction of axis y at the beginning. So v0 is equal to 0 in this case. So this expression is also equal to 0. And there is acceleration in the direction of the axis y, but acceleration vector is directed is opposite to the axis y, so its coordinate is equal to minus magnitude of this vector. Magnitude of acceleration is equal to g, so here we have minus g. So we can write equation of motion for the axis y. Y equals to h minus g times delta t squared divided by 2. So we have these two equations of motion, and we want to find the equation of the path of the front body in the coordinate system y x. So we have to get rid from these two equations delta t. We will transform this first equation and calculate from it delta t. It's done here. Next we put right side of this equation here, it's done here, and change form to such. So now we have equation of the path of the front body in the coordinate system y x. Now, to find the place where the front body hit the obstacle, we should add to this equation describing the obstacle. Let's start with the horizontal platform. Equation of this line is y equals to b. So it's enough to put instead of y, b, and calculate from this equation the value of x. Of course, we should take this expression to the left side. There will be plus in front of this equation, this expression on the left side, and b we take to the right side. It will be minus b here. So we have a quadratic equation, and this equation has a solution only if h is greater than b, because x squared is positive, so this difference h minus b also has to be positive. Of course, if h is greater than b, and the difference between h and b is greater than 0, then we'll have two solutions, one positive and one negative. this negative solution is the point where this line, it is parabola, is crossed by this straight line. This positive solution is the solution we are looking for. If b equals to 0, then equation of the obstacle is y equals to 0. It is equation of the axis x, and coordinate x of this point will be just the range, the distance in the horizontal direction from the point of throwing the body. So, if y equals to 0, we put here 0, 0, and then x equals to distance, this distance. So we put here d, and we calculate d from this equation. We change side of this expression to the left side, and calculate d. We here also have two solutions, and only the positive solution is the one we are looking for. We know that in the direction of the axis x, no force is acting on the body, so this body is moving in this direction with a constant speed v0. So distance d is equal to v0 times delta t. We calculated this distance here, and comparing these two equations, we see that delta t is equal to this square root. So we calculated also the time of the motion of this body. If our obstacle is vertical wall, its equation is x equals to c, then we just put here c, and we calculate value of coordinate y of this place. If our obstacle is a slope, so its equation is y equals to tangent beta times x. So we put here tangent beta times x. It's done here, and we change side of these two expressions to the left side, and we have here, and we have a quadratic equation, and we calculate roots of this equation, and the greater root is the value of coordinate x of the place where these two lines intersect of this point. So we have solved our problem, and it's the end of this lesson.